Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. In the last episode, we examined several well-defined systems of molecules where we could quantify entropy explicitly, and explored the formal definitions of temperature and pressure as thermodynamic properties. An important implication of these definitions is that changes in internal energy, entropy, and volume of a system are related through temperature and pressure. This leads to a general prescription for measuring entropy in real systems of molecules where molecular interactions are too complex to count the multiplicity theoretically. Specifically, I suggested that changes in entropy could be related to heat flow under a specialized set of conditions called a reversible transformation. We've talked previously about macroscopic reversibility in the context of pressure-volume work. But what exactly does it mean? And how does it impact how we formulate the second law for this purpose? Recall that to relate heat and work to changes in internal energy, we've used various forms of the first law. Likewise, you might expect that to predict changes in entropy, we ought to be able to use the second law. As we've discussed it so far, the second law states that the entropy of an isolated system can only increase. That's great, but what if we don't have an isolated system? As we've seen with the first law, we're often interested in closed or open systems. How do we likewise formulate the second law for practical purposes? This question reminds me of another bad joke. 3 chemical engineering students are riding in a balloon and get lost in the fog. Hoping to find a landmark, they start yelling toward the ground.
Hello!
Whoa! Hello!
Is anyone there?
Where are we?
Where are we?
Hello?
They yell for hours, but nothing, no reply. So they give up and wait. Finally, the fog begins to lift, and they look around to try to regain their bearings. Suddenly, they hear a voice from below.
You're lost! Look around and try to regain your bearings!
One of the students turns to the others and says, "Clearly that was a chemical engineering professor." The others say, "How do you know that?" "Well," says the student, "the provided solution is entirely accurate and obvious, but it took too long and didn't actually help." Of course, I know none of you feel that way. In any case, the analogy here is that the second law, at least as we've been discussing it so far, lacks general utility as an analysis tool. In contrast, think about the first law. It states that the energy of an isolated system can neither increase nor decrease. On its own, that's not so useful either, but by introducing a control volume, defining internal energy, and describing energy flows in terms of heat, work, and mass enthalpy flows, we were able to formulate useful forms of the first law that apply to closed and open systems. So what about the second law? What are the equivalent expressions for isolated, closed, and open systems that embody its more general meaning? Using similar conservation principles, we might expect that changes in entropy of a system can be linked to heat, work, and mass flows. But we have a problem. Unlike internal energy, entropy is not a conserved quantity. It can increase in an isolated system. In other words, it can be generated. One way to say this mathematically is that delta S equals Sgen for an isolated system, where Sgen is greater than or equal to 0. For closed and open systems, this potentially throws a wrench in the works of any conservation principles we try to apply to track changes in entropy via flows across the system boundary. So what exactly do we mean by entropy generation? What processes are expected to produce entropy, and what conditions are needed to ensure that it is not generated? We can try to understand entropy generation in a couple of different ways. The first is to consider what happens on a molecular level, specifically how we expect the multiplicity of a system to change when transformed via heat and work. To explore this, recall our previous example of a quantum ideal gas. In this model, the gas is represented as a large number n of non-interacting particles in a box, with 3 translational degrees of freedom, or modes, corresponding to motion in the x, y, and z directions. As described last time, due to quantum mechanics, the energy contained in each mode cannot vary continuously, but must adopt a discrete value, E sub I, corresponding to the integer value of the translational quantum number, L sub I, for that mode. Imagine that our system of quantum mechanical particles is initially at equilibrium at temperature T and internal energy U. How will this energy be distributed, on average, amongst the available translational energy levels? Some of you who have taken PChem may remember that for systems of molecules at equilibrium, the relative probability of an energy level being occupied follows a Boltzmann distribution, which predicts that the relative probability P sub I that a given energy level will be occupied is given by e to the minus e sub I over kBt, where kB is Boltzmann's constant. One way to visualize this probability distribution is to shade each level in proportion to the probability that the level will be occupied. Here I've used varying intensities of red to indicate this probability. At the temperature chosen here, energy levels above L equals 20 have very little probability of being occupied, while energy levels near the average, level 8 in this example, have a high probability of being occupied. By adding up these individual probabilities, known as a partition function, and calculating the weighted average of the energy, we can predict the average energy content of each translational mode. This calculation predicts an energy of 1/2 kBt per mode. Since there are 3 translational modes in the x, y, and z directions per molecule, this corresponds to an average energy of 3/2 kBt per molecule, or 3/2 RT per mole. This agrees nicely with our previous calculation of the molar heat capacity, 3/2 R, based on the entropy. Now imagine we increase the energy content of the system while maintaining a continuous state of equilibrium. According to the fundamental property relation we derived last time, we have 2 ways to do this. The first way is to keep the volume, and thus the box size, A, constant. If we keep the value of A constant, then the energy levels, which scale as L squared over A squared, remain fixed. This means that the only way to increase the energy content of the system is to transfer individual quanta of energy from the environment, thereby increasing Lx, Ly, or Lz of the individual molecules. As shown in this cartoon, this corresponds to an increase in the relative probability of finding the translational modes at higher energy levels. Or vice versa if we transfer energy from the system back into the environment. As we discussed in the previous episode, increasing the occupancy of higher energy levels increases the number of ways the energy can be distributed within the system, and thus also increases the entropy. This is the quantum mechanical interpretation of what it means to transfer heat under conditions of equilibrium. Although our model here is for an ideal gas, this fundamental connection between heat flow and changes in entropy under equilibrium conditions is universal to any system of molecules. As an alternative, let's now consider what it would require to change internal energy with no change in entropy. Based on our quantum mechanical picture, it would require that the average populations of all the energy levels remain exactly the same during the transformation. But how can we change the energy of the system without changing the populations of the energy levels? The only way would be to change the energies E sub I of the levels themselves. In this case, the energy of each level is inversely proportional to the square of the box size, A. So if we decrease the volume in a continuous state of equilibrium, we'll raise all the energy levels together, increasing the total energy and temperature of the system. Or vice versa if we increase the box size. This is the quantum mechanical interpretation of what it means to do work under conditions of equilibrium. Note that these relations between heat and entropy, and between work and volume, are predicated on the system being in a continuous state of equilibrium during the transformation. But what happens if it isn't? To understand this, imagine we start with our gas in its most compressed state at high internal energy, and we then increase the box size without transferring any heat or work to the environment. This is similar to the case we studied earlier in the course, where a gas is confined to one side of a container by a membrane and then released into a larger volume. What will happen? Based on our quantum mechanical picture, an increase in the box size, A, corresponds to a lowering of the energy levels. But in this case, we're not allowing the energy contained in these levels to leave the system. Meanwhile, we're moving a bunch of empty levels into the same energy range as the ones that are already occupied. So as you might imagine, as soon as we release the gas, dropping these levels, wham, this energy will just spread out into all these new translational states via level crossings and collisions. The total energy content remains the same, as does the temperature associated with the Boltzmann probability distribution. However, due to the massive increase in the number of available energy levels, the multiplicity, and thus the entropy, is much greater, in accordance with the second law. Thus, for this transformation path, work and heat, which are both zero in this case, have no relationship to changes in volume or entropy. An interesting follow-up question is whether we can perform this transformation backwards. According to the second law, the answer is no, since entropy cannot spontaneously decrease. With this quantum mechanical picture, we can see why. In order to restore the original positions and populations of the energy levels, we need to deoccupy energy levels. There's no way to force the molecules to do this spontaneously. Instead, we must transfer individual quanta of energy from these molecules to the environment, which requires export of heat. And then subsequently, or in parallel, we need to raise the occupied levels back to their original positions, which requires input of work. The minimum amount of heat and work required to restore the system to its original state corresponds to an equilibrium path. The unrestrained expansion of a gas into a larger volume is an example of an irreversible transformation, so named because of the inability to perform it backwards via equal and opposite flows of heat and work. One hallmark of an irreversible transformation is that the system departs from equilibrium. Unrestrained expansion of the gas involves significant gradients in pressure and temperature, so is not in equilibrium along the entire transformation path. Another hallmark of an irreversible transformation is the generation of entropy. In the classical view, this entropy is created by unrestrained expansion of a gas into a larger volume, increasing multiplicity. In the quantum mechanical view described here, this generation can be traced to the spontaneous spreading of energy into new energy levels without an associated transfer of heat to or from the environment. A second, perhaps more general way to think about entropy generation is macroscopically, based on the thermodynamic definition of temperature as du ds at constant V. Specifically, recall our previous thought experiment involving heat flow between two systems A and B. We found that if the temperature of both systems is the same, no entropy is generated by flow of a differential quantity of heat, dQAB, from system A to system B. The entropy of each subsystem individually does change by an amount given by plus or minus dQAB over T. However, these changes are equal and opposite, and can be linked to the inward or outward flows of heat into or out of each subsystem. So for the combined isolated system A plus B, delta S is 0, and thus according to our statement for the second law for isolated systems, S gen equals 0. However, if TA is greater than TB, the net entropy change is positive, given by the difference in reciprocal temperature between systems B and A. Since the combined system is isolated, this entropy must have been generated inside the combined system. But where exactly is this new entropy created? And where does it reside within our system after it is generated? To address this, imagine that the heat transfer occurs slowly under quasi-steady conditions, such that the temperature profile is linear inside the metal conduit. In this scenario, systems A and B only see the end of the metal conduit that shares the same temperature as the system. Thus, from the perspective of each system individually, the increase or decrease in entropy is associated with heat flow into or out of each system, not entropy generated inside either system. This implies that the additional entropy must be generated inside the conduit. This can be understood by examining a slice of conduit of width dx. As with the overall increase in entropy of the combined system, we can express the differential entropy produced within dx as dQAB times the difference in reciprocal temperature across the differential slice of the conduit. In other words, each differential slice of the conduit generates a tiny bit of entropy, which is proportional to the derivative of 1 over T with respect to x. Integrating, we find that the total entropy generated within the conduit by this heat transfer process is equal to the total entropy increase of the combined system A and B. Since this is a steady-state process, the entropy of the conduit cannot change with time. Rather, this additional entropy is transferred via heat flow into system B, which experiences a net increase in entropy greater than the decrease in entropy of system A. This association between entropy generation and gradients turns out to be a generalizable conclusion. Entropy will be generated wherever and whenever a relaxation process occurs in response to local gradients in temperature, pressure, or composition. Okay, so returning now to our original question, how do we incorporate these concepts of equilibrium and irreversibility into our formulation of the second law for closed and open systems? To answer this, consider an isolated system surrounded by another thin boundary region, B, with spatially uniform temperature, TB, and pressure, PB. What's happening deeper inside the system is unclear. There may be gradients in temperature, pressure, or other variables which generate entropy. However, let's assume these gradients are macroscopic and don't involve any discontinuities at the boundary. Thus, within the boundary region, the molecules can be considered in a continuous state of equilibrium locally. Now imagine that while maintaining the inner part of the system in isolation, we take the boundary region out of isolation and flow differential quantities of heat, dq, and work, dw, across the outer boundary. During this transformation, we maintain the boundary region in a continuous state of equilibrium. In other words, a reversible transformation. Based on previous considerations, we expect the entropy of the boundary region to increase by an amount dsB equals dq over tb. Meanwhile, according to the second law, since the inner part of the system remains isolated, the only way for entropy to increase there is to be generated. Invoking the fact that the entropy is extensive, we can say that the change in entropy S of the entire system, including the boundary region, is ds equals dq over tb plus ds gen, where ds gen is greater than or equal to 0. Following this step, we turn the heat and work off, re-isolating the system. At this point, it's possible that the boundary region will no longer be in equilibrium with the rest of the system, and thus the system will relax to a new state via internal flows of mass and energy. However, according to the second law, since the combined system is isolated, any further relaxation processes that do occur can only increase the entropy further, not decrease it. Thus, even if our introduction of heat and work creates internal gradients, we can still say that ds is dq over tb plus ds gen, where tb was the temperature of the system boundary where and when heat transfer occurred. If we now consider that the boundary temperature Tb can be a function of time and or position along the outer surface, the total change of entropy of the closed system will become the time and or surface integral of dq over Tb plus the total entropy generated inside the system, Sgen, which must be greater than or equal to 0. This equation shows that if our entire system remains in equilibrium during a transformation, and thus Sgen is 0, delta S of the system can be related to heat flow across the system boundary. In contrast, if heat flow is 0, any entropy changes of the system must be associated with entropy generation inside the system. The equation we just derived is a general statement of the second law for closed systems, provided we have a well-defined boundary temperature Tb where heat flow is defined to occur. Using an analysis similar to the one we examined in episode B3, we can also derive an analogous statement of the second law for open systems at steady state. As with the closed system, Tb is defined as the temperature at the system boundary where heat flow occurs. Entropy can also flow into or out of the system via convection of mass. We'll come back to open systems a bit later when we consider issues of process efficiency. For the moment, let's focus on closed systems, in particular the use of the second law to quantify the entropy of substances via measurement of heat and work. Recall episode B4 where we used the first law in conjunction with hypothetical transformation paths to relate changes of internal energy to measurable properties, such as heat capacity and other thermal properties. It turns out we can do exactly the same thing for entropy. The revised argument goes something like this. Let's say we have a substance in a closed piston cylinder assembly at a particular well-defined reference state. As we did with internal energy, at this point we define S to have a particular value S0. Like internal energy, the choice of the value of S0 is arbitrary, so in many cases we just choose it to be 0. Now imagine we add or remove heat and or work until the system reaches a new equilibrium state that we care about with temperature T1 and pressure P1. As with internal energy, we can carefully measure the differential quantities of heat, dq, and work, dw, per mole that we add to the system at each step along the transformation path from state 0 to state 1. Writing out the second law for closed systems in intensive form, we see that to quantify and integrate changes in entropy, we would need to know the heat flow, the temperature of the boundary of our system, as well as the differential amounts of entropy generation, ds_gen, that are created inside the system. Is it possible to measure this generated entropy? This finally gets to the heart of our problem. To see this, let's take a look at an example you've already thought a little bit about on one of the problem sets. In this problem, you compared the isothermal expansion of an ideal gas via two different paths. In the path shown on the left, the gas is initially constrained to have volume V1 by a membrane. Upon rupturing the membrane, the gas spreads out into a larger volume V2. Because this process involves no heat or work, the total change in internal energy is zero. Since U is only a function of T for an ideal gas, this path must also be isothermal. In the path shown on the right, the gas is initially constrained to have volume V1 inside a piston cylinder assembly. The gas is then slowly and isothermally expanded to a larger volume V2. Since U is only a function of T for an ideal gas, this path must be isoenergetic, just like the path on the left. However, heat and work, which due to the first law are equal and opposite, are both non-zero. Although these two paths are different, entropy is a state property, so delta S must be the same in both cases. Recalling that the entropy of an ideal gas scales as the log of volume, we already know in this case that delta S is R log of V2 over V1. However, what if we didn't know this? Would we be able to measure this difference via heat and work flows, as we described earlier? Focusing on the path on the left and invoking the second law for closed systems, we can say that the differential changes in entropy of the system will be a sum of differential heat flows across the system boundary divided by the temperature at the boundary, plus differential quantities of entropy generated inside the system. Since in this case there's no heat flow, the only way for the entropy to change is if it is generated inside the system. Thus the total entropy change, delta S, is entirely generated entropy. We have no information about what's going on inside the system, so from a measurement standpoint, we have no information to determine the amount of this generated entropy. In contrast, if we examine the path on the right, according to the conditions described, we don't have any gradients in temperature or pressure inside the system during the transformation. Thus, if we make the same second law statement, the generated entropy is zero, meaning that all entropy increases can be attributed to the incoming heat flow. Meanwhile, since there are no gradients inside the system, the boundary temperature is just the same as the bulk temperature T. Using the first law, we can re-express the differential heat as differential work, which is minus PdV. Substituting the ideal gas law and integrating at constant temperature, we find that the total change in entropy is R log V2 over V1, corresponding exactly to what we know the entropy change is for this substance. In other words, even if we lacked a theory for the entropy of the substance inside the piston cylinder assembly, we would still have been able to measure it via heat and work flows. To summarize the situation, the transformation path on the left is irreversible. An irreversible transformation is defined as any transformation that involves gradients of temperature, pressure, or composition inside the system. These gradients result in entropy generation inside the system that cannot be accounted for via heat flow across the system boundary. The reason this type of transformation is called irreversible is that due to the entropy generated, it cannot be performed backwards by an equal and opposite flow of work and heat across the system boundary. In contrast, the transformation path on the right is reversible. A reversible transformation is defined as any transformation in which the system is in an internal state of equilibrium at all times. Since there are no gradients, there's also no generation of entropy inside the system. The practical consequence of this is that all changes in entropy can be attributed to flows of heat across the system boundary. The reason this type of transformation is called reversible is that it can be performed backwards by an equal and opposite flow of work and heat across the system boundary. Over the years, I've found that students often get confused about the distinction between a change in entropy versus generation of entropy. For example, misstating the second law as delta S must be greater than zero. What I hope these examples clarify is that entropy, just like any other state property, can go up or down depending on the state of the system. Delta S being greater than zero does not necessarily mean that entropy was generated, since part or all of that increase may have been the result of reversible heat transfer, which results in an equal and opposite decrease in the entropy of the surroundings. Likewise, delta S being less than 0 does not mean that entropy was destroyed, violating the second law. It just means that the system evolved some heat, and this evolution of heat caused the entropy of the system to decrease. Finally, I'd like to draw a distinction between the concept of a reversible transformation, as we've been discussing it here, and a reversible process, commonly defined in textbooks as a process that does not generate any entropy, and thus can occur in either direction. Is this the same thing as a reversible transformation, or path? According to many textbook authors, including the author of our own book, the answer is yes, these are the same. However, a truly reversible process is impossible to achieve. Any work we do or heat we transfer requires a gradient to exist somewhere, sometime, even if those gradients exist outside the system of molecules we care about. For example, imagine that we measure the change in entropy of a non-ideal fluid via heat flow during an isothermal expansion. We do so very slowly, such that the fluid is maintained in a constant state of equilibrium during the entire transformation. However, to get the heat into the fluid, we need to transfer that heat from a heat source. This involves gradients in temperature outside our system, so generates some entropy there. Also, imagine that the work we do during the expansion is stored in a perfectly reversible set of rechargeable storage batteries. But a month later, we discharge these batteries in a device, generating heat which ends up in the environment. Does the entropy generated by these irreversible process steps invalidate our assumption that the transformation path of the fluid was reversible? The way most authors resolve this question is to sidestep it by imagining a hypothetical situation in which no irreversibilities exist anywhere in our process. I personally don't find this explanation very satisfying, since it seems to imply that the entropy is not really measurable in any real system. It can only ever be inferred as a theoretical construct. In my opinion, the better answer to this question is that any irreversibilities in our process that occur outside the system, such as the heat transfer to the cylinder or the discharge of the batteries a month later, do not involve generation of any entropy inside the system. This means that we can still attribute changes in entropy of the system to heat flow across the system boundary. In other words, the measurability of entropy does not require that the process as a whole is reversible, only that the transformation path of the molecules inside our system is reversible. This condition can be easily met under real-world conditions. The reason we don't commonly measure entropy ourselves is not because it's impossible to measure in real systems. It's simply that we don't have to if we or others have already measured the heat capacity and PVT properties. But that's getting into the devilish details, which is the subject of the next episode.